Well, why don't we just start with a few reflections from yesterday. I thought we heard some amazing speakers and learned a lot and really amazed actually by how well everything went. So thanks to everyone who spoke, and wondering if anyone had any sort of aha moments or moments of clarity or anything else that occurred yesterday when you were participating. Any big picture thoughts or mind-blowing ideas?
Bruce has his hand raised.
Okay, Bruce.
Yeah, I just wanted to say I was really struck by the fact that the electricity use was going to, on average, grow much faster than previously. Not because of data centers, just because of the electrification of everything. So that was something I really hadn't been thinking much about. I've been mostly looking at historical data. So certainly the average is going to go up. And then, of course, the data centers are the local issue more, but the growth of electricity use going up, I think, was a bigger thing for me.
Great, thank you. That's a really important point. Others, yes.
From our discussion of the different topics and ideas, I think it was interesting to see how each of the groups sort of, I almost couldn't contain themselves. It's hard to stay narrowly focused on one
Yes.
topic because all of these issues are so intertwined and connect to so many different sectors. And so I think even if there was an attempt to try to have a narrow focus, everyone sort of inherently kept expanding and kept saying, well, we need to include them, or we need to include this, or we need to, factor that into the tool or the demonstration itself.
So I think that's both a good and a bad thing. I mean, I think it's great that everybody wants to solve all these problems simultaneously, but I also think it's something that we'll need to warn DOE about in terms of trying to keep things narrow enough that you can succeed. And so that's actually a potentially even recommendation that could come from us, because it seems like it's easy for people to get excited about all the connections between these things, and possibly that might be a weakness at some level. Other thoughts?
One thing that struck me was that, talked about overlapping networks of water, gas, electricity, data, and it is all these different institutions that have a role to play. And the complexity gets kind of overwhelming at a certain point. So I think that the most successful solutions may end up being the simplest if we can make things as simple as possible. That might be useful.
Great. Other thoughts? Heather. Oh, Heather.
Thank you. Just on the first part about sort of future demand, I had a curiosity around the accuracy of sort of past forecasts. I've looked quite a bit at water forecasts, for example, and there has been a tendency to overestimate sort of future demand. And so I just was sort of curious about the extent to which that has been seen on the electricity or the energy side. And then it also further, I think it came in one of the discussion around decision-making under uncertainty. And so how we sort of, given a very likely uncertain but variable energy and water demands, how we kind of best build a system that allows for greater flexibility.
Thanks for bringing up the decision-making under uncertainty. I note that the one idea along with that got only one vote yesterday, and yet it seems to me that we couldn't possibly be in a more uncertain moment in our lives or the history of our country. And so it's kind of interesting to me, like how are we don't know, for example, whether this electrification process is actually going to proceed. And so it seems to me that there is a very broad set of possible futures. And, it's not new news that there's uncertainty, but I'm just wondering in this context, how we might be able to think about that. Go ahead.
You've got to prepare a few more options than you're actually going to use, I think, sometimes.
Any other thoughts?
I mean, I think it just comes down to scenario analysis. You know, I think EPRI had, you know, I think showed 17 or 18 different scenarios in your future outlook. When NREL, we do our standard scenarios, we have over 100 different future electricity scenarios we project. None of those will be right, you know, none of those will be correct, but at least gives us bounds on what to look for. But I mean, at the same time, you know, Noah, you know, if we were here 15, 20 years ago, none of us would have been predicting the shale boom. All of our projections would have been very different, a very different role for gas. So I think that's just inherently part of the nature of doing these forward-looking projections, is you know you're gonna be wrong.
Yes, great point. Yes,
I know this is a challenging one to talk about without going too deep into the policy realm, but I think the other thing about a lot of the uncertainty here is that the futures that we end up with, especially on some of the electrification and energy things, are pretty dependent on the future that we want. And it's really easy to say that, like, moving forward, a particular future is purely a policy outcome, but sort of from a scientific perspective as well. If we're talking about climate change actually being a major threat, we do know from a lot of modeling that there are some futures that work for mitigation and there are others that don't. And so thinking about this as it is deep uncertainty if you just sort of assume that anything could happen. It's much less deep uncertainty if you're trying to reach a goal. Some of that is policy, some of that is actually a scientific assertion that this has to be where we're trying to get to. And so I'm not sure exactly how we want to think about that, but it does strike me that the possible set of futures does depend a lot on what we're trying to do.
if we can all agree on what that is, that would be helpful. That being said, I think what your point that you just made, that, you know, if you have a goal and you stick to it, there's a whole lot less uncertainty because people have agency. I mean, they can make decisions, and if one path isn't working, you can adjust your path so long as you do know what your goal is. But that sort of brings in a whole bunch of decision science and other components, but good point. It's not like we're just victims of all this, you know, uncertainty.
Right.
Go ahead.
Yeah. So I know I proposed to have that original planning simulation tools, got only one vote, but anyway, I still think it is a very useful tool because, for example, right now we work with NREL to develop the tools and also work with NAWI. NAWI developed also a lot of tools. When we talk about the risks and the uncertainties, of course, we can have scenario analysis. There is also sensitivity analysis, and then it will tell us what factors could be critical. If we change this variable, what would be the impact on the entire system? Maybe that will help us to prioritize the impact factor of these variables. And yesterday, I also learned actually it's this study is for energy water nexus. And then Rick has a really good point is to look at resource recovery, because the water has a lot of resources and chemicals that we can recover, and also waste management related to all these alternative water uses for fit for purpose applications. And I think yesterday's meeting was very, very exciting, and I learned a lot. Thank you for all the speakers and the discussions.
Sure. Go ahead.
So I guess I would add is, Emily, thinking about what you just said, and Jordan, thinking about the modeling. I mean, the modeling points to potential futures, and then we're thinking about where we should go. One thing that struck me yesterday, though, both looking at the power sector side and the kind of produced water side, is kind of the lack of resiliency that's there. And I think that is developed more and more. So like, I think if you were to be having this conversation 10 years ago, some of those things were on the horizon, and we haven't really gotten past kind of a critical point, but we're really at a point where there's a lack of resiliency. I saw that yesterday when we looked at the power side, and you see the vulnerability of the grid. You've seen the times when we've had blackout events just having happened, most of them in the past 5 years, where we've had to call in the, what we call it, Kurt, where basically we can stop environmental compliance to keep the lights on, sort of thing. We've had to invoke that.
You get exceptions on air.
Yeah, like that's been invoked by the power industry more in the past like 4 years than it has been in the past 30, sort of thing. And talking about produced water and there being this, you know, very finite amount of pore water space and getting towards those limits. So to me, that's just, again, pointing to a critical driver of why we're doing this, because it feels like we're kind of right on the edge.
One who pays for resilience, I think the electrical grid of 40 years ago was designed by engineers. The electrical grid today is designed by engineers, but the decisions are made by finance people very much more. And so all of our infrastructure is optimized financially to be the minimum it can be and still to provide the function. So we've engineered resilience out of most of our systems. So when you take an overstrained system and you overlay 3 or 4 of those different things, it gets a little bit scary.
Okay, that's cheery.
All right.
Yes, Jordan.
Yeah, I was just gonna say, I think. One comment that I guess it was Dr. Overby made is that. The systems are designed to run at as high utilization as possible, right? So you wanna push the system as close to its capacity as possible to avoid overbuilding, which would increase costs for consumers. And then I would argue, not strongly, right, but like flexible enforcement of environmental standards is a source of resilience, right? It's institutional flexibility could be part of what we inevitably sort of have to bake into the design of systems in the future if we're going to deal with, you know, exceptional events.
I mean, I guess it's a form of resilience if you're a person, but if you're a fish that's about to be boiled in your river, that's
Right.
maybe not so much.
You know, yeah.
Anyway, yeah.
Maybe a slightly different perspective about the breadth of the project, it being too broad. Maybe if you think about it as a challenge where there's multiple teams with the same common goal, each achieving and then coming together at certain moments in time, as compared to the typical academic model, which is a team that's doing the task, that has some real value to it. In an ecological forecasting grant from NSF, you know, the model initially was exactly that. And then once it became a distributed problem with people solving pieces of the whole and then coming together to figure out the interaction scenarios between them. And then instead of one modeling scenario, you bring together a myriad of modeling scenarios and then, you know, get to what Pei was talking about, where you look at sensitivity analysis between them. That seems like a strategy that puts all of it together, but in a different way than we normally go about it.
Great idea. Well, those are excellent thoughts. If you have more excellent thoughts, please share them later. We're going to go ahead and stick more or less with our agenda here. And so this session is about biofuels at the intersection of the water energy nexus. And we have Ashlyn in charge of the performance.
Yeah,
So it's all
the
yours.
performance. It says moderator, but I didn't know I was performer. This, yes. Thank you, everyone. I appreciate your perspective, and I'm really excited to moderate this panel today because I think this is going to be a very different conversation around water quality and water quantity than what we had yesterday in relationship with biofuels. One quick adjustment from your agenda. We're gonna switch some of the order and we're actually gonna go David, Ted, VJ, Jonathan, John, and he'll be online. So we'll start with some discussion around the water perspective, then go to the biofuels perspective and start to formulate our thoughts around this water energy feedback loop as it emerges. So David Sportney is going to kick us off. He is a professor at I'm looking at your bio, Civil and Environmental Engineering, and also the Department of Chemistry. I forgot that part, at the University of Iowa. So we will hand it over to you. And just like yesterday, we'll let all of the speakers present and hold questions to the end, and then have more of a roundtable panel discussion.
Well, while Brian's getting my slides up, I'll just say I come at this largely from the perspective of water quality, which is my expertise,
but I've done a lot in terms of environmental policy and also public health. And so some of the things that I'm trying to focus on, I figured I would come and talk about things that I think are overlooked with regards to how we're doing biofuels, their impacts on water quality, is also water quantity. And so, yeah, overlooked and emerging challenges, and I'll do my best to stick on time, so go ahead. So I'll do this and save Ted, where we lead the US in ethanol production, 42 corn and 2 cellulosic plants, more than 4.1 billion gallons, or nearly 1/3 of all US ethanol. That's taking 1.3 billion bushels of corn, so that's about anywhere from 50 to 70% of Iowa's corn production in a given year. 70% of our land is in a corn-soy rotation, and about 20% of our land is used to grow corn ethanol. So when we talk about our production system in Iowa, it really is driven by biofuel production. Next slide. And I want to say, like, we've known for some time, there's a lot of focus on nutrients. And so one of the things I want to try to do is expand that conversation. So this was 2008, and this is Donner and Kuchar. It talks about the projected expansion of corn-based ethanol. It's basically going to make achieving our goals for things like the Gulf Hypoxia Task Force and the reduction of Gulf hypoxia practically impossible without radical shifts in feed production, diet, agricultural land management. And unfortunately, since this has been published, we really haven't made the gains that we're hoping to make in that space. Next slide. And so while there's been a lot of conversations about nutrients, I think that's appropriate. We want to think about maybe a little bit of a broader lens on some of the challenges in water quality that have come along with this production system. So these are the overlooked challenges that really come from unique discharges that we have as a part of this production system. So for example, we use a lot of agricultural tile drainage in Iowa. So Iowa was originally a marshland effectively. And so the first place to drain the swamp, or one of the first places, was Iowa. And we did this using these tile lines. And so we've been working with landowners in southeast Iowa to sample water that's coming out of these. And then we've also been working with a landowner that has 2 drainage districts. And Ted will talk more about the drainage districts, but these are actually draining large segments of the land now. And we have drainage districts that oversee this infrastructure. And so this is more of like a watershed scale snapshot, whereas this is the individual farm snapshot. And for perspective, this stuff is all going into Des Moines Waterworks source water. So next slide. Absolutely, there's nitrate. And I don't really want to talk much about nitrate because we know this. And so on an individual farm, this farmer here was losing about 42 pounds per day of nitrate as N. The economics of that don't make an awful lot of sense in terms of how much nutrient loss they're having. At the drainage district scale, we see a similar story. Earlier in the season, after spring application of manure and anhydrous, you're getting close to 35 milligrams per liter as N coming through the drainage districts into TED source waters. Remember, the drinking water standard is 10. And so that's the baseline we have. That's a protective standard. It's an acute toxicant in drinking water. These drainage district lines end up going on to be like basically source water for our rivers and streams that make up our surface waters in Iowa. Next slide. But what I want to point out is and we're finally just beginning to talk about this, they move a lot more. So one of the things that is constantly amazing to me in Iowa is the amount of products we put on the land as a result of this production system. And so we've been specifically focusing on neonicotinoid insecticides. These are ones that have been linked to colony collapse disorder in pollinators. And we basically can't find a tile line sample that doesn't have things like clothianidin, thiamethoxam. These are used in seed treatments. And so if you purchase seeds to grow biofuels, like corn, you get these beautifully colored seeds, and then there's an insecticide, a nematicide, a fungicide, mixtures that then make their way into those same tile drain systems. And so we can measure through time that basically our baseline for the water quality coming off our production system is at the US EPA aquatic invertebrate chronic toxicity benchmark. I would argue that we probably need to figure out how to do a production system that's baseline isn't chronic toxicity for our invertebrates that's harming our biodiversity. Next slide. We're also interested in the discharges that are coming out of the production of corn ethanol. And so this is the standard sort of workflow that you might see at a dry mill facility. Next. And if you think about the chemical inputs that go into this, I think we're primarily interested in where the pesticide residues might go. And then the other thing we discovered is that we actually use antibiotics in the actual bioreactor systems like virginiamycin or penicillin. And they do this to control growth of unwanted bacteria in the bioreactors during the ethanol production process. There's other things that go into it, but our interest is really those 2 pieces. Next slide. And so what we're finding is that the waste streams that come out of these are dry mill facilities. We sampled 4 in Iowa, working with USGS. And if you look at what their discharge permits are for, it's for what you might expect, reject water from RO, cooling tower blowdown, softener reagents, but you do see pesticide residues, including 18.1 micrograms per liter of AMPA, which is a glyphosate metabolite, so that's a pretty significant amount. And then we also do see bacterial signatures, total coliform is an indicator bacteria, but probably more concerning is that we do see antibiotic resistance in some of those bacteria that are likely tied to the use of the antibiotics in the production process. So I would argue this is a more complex waste stream that probably deserves more attention than we've been giving it. Next slide. So now I want to talk a little bit about what's actually happening right now in Iowa that are more of these emerging trends beyond the quality piece and thinking a little bit more about quantity. Next. So right now, everything is the push to try to sustain corn ethanol as sustainable aviation fuel. And so this was an article in the New York Times that talked about the water demand that's going to come with that. Next. What I'll say is in Iowa, we've basically tied the future of corn ethanol to the ability to do carbon sequestration. And so the big debate has been places like Summit Carbon Solutions that want to build pipelines across Iowa to move the sequestered CO2 to the Dakotas where it can be deep well injected. But this has just happened this month. Our Senate and our House passed a bill that would restrict eminent domain that is threatening the potential to secure the easements that's needed to build these pipelines. And right now there is strong push on Governor Reynolds to veto that bill, and it's sitting at her desk at this moment. And there's no bones about it. The ethanol industry is basically saying, if we don't get this, we're going to fall behind here in Iowa. We need to maintain corn production through having pipelines. Next slide. The other issue is that people are beginning to worry about the amount of water use that goes into carbon sequestration. So this is a Sierra Club chapter report. It received attention in the news. And if you could click forward. Some of the headlines are like, Summit was obtaining water withdrawal permits from Iowa DNR to about 55.9 million gallons per day for one of their carbon sequestration facility. I think there's 31 sequestration facilities in total that they want to produce. And so you can think about how the water use and water demand will scale. Next. The other thing that's getting a lot of attention lately is Iowa has the largest soybean crush capacity of any state. And so uses of soybean is increasing, particularly for soy-based biofuels. We see that in Iowa, we have a nameplate capacity of about 1.3 million bushels per day, or about 420 million bushels per year. Next slide. And so we know there's water use that goes into that and wastewater that will come out of it. And so this was an industry-based report from the National Oilseed Processors Association that talks about the water consumption that's coming from crushing as well as the wastewater discharge. And so if you do the math on what our nameplate capacity is, this is about the amount of wastewater that would be produced by about a 15,000. The city of Newton produces that much waste in a given day. So things to consider as we push for soybean crush facilities and reaching that capacity. Next slide. So since we only have a few minutes, hopefully I know that was a lot and kind of fast, but my take home thoughts, and these are just mine, I'm happy to defend them. I think we cannot achieve desired environmental outcomes with the status quo of biofuel production in Iowa. I would say we're already missing that. I think the focus on nutrient loss is absolutely appropriate, but at times it distracts from the wider range of chemical and microbial water quality challenges that can be associated with biofuel production. Overlooked challenges are linked to unique and poorly characterized discharges from ag drainage and biofuel processing waste. I think the emergence of CO2 sequestration and growth of soybean-based fuels is going to increase water use and present new water quality challenges through the waste that's generated. Next slide. And so since we were trying to think about recommendations and maybe even more of a technology focus, here's my list. I mean, the first thing, conservation compliance. We should be tying USDA benefits like crop insurance to environmental outcomes. We did this with Swamp Buster and it worked on highly erodible land. There's no reason regulations will work, and this would keep a lot of these issues out of our water quality. I think we need to make precision ag more precise. Seed treatments were marketed as being a more precise form of agriculture because the pesticides are delivered where they're needed, but they move. We lose them. They accumulate in soil. They wash off. So we need to limit that use. And at the same time, that would help the producer's bottom line. The amount of product they're losing is hard to rationalize. New end-of-pipe technologies for drainage management. Every engineer wants to put a widget at the end of a tile drain, but I would caution, is it a pipe drain? When you actually go out and sample on farms, there's just so many discharges. And we also know that things like conventional bioreactors, wood chip bioreactors, we probably can't scale them to the size necessary. Continue efficiency gains in biofuel processing and shift the focus to emerging production trends like these soy crush facilities. Improve monitoring and treatment for waste, and so aspiring for things like zero liquid waste discharge. And then, most of that water and CO2 sequestration is for cooling. So what can we do to think about reuse, other ways to minimize water use for cooling for sequestration? So those are my thoughts. I'm happy to talk more, and I am at 10 minutes. So thank you.
Thank you, David. Really appreciate it. Excellent overview. Our next speaker is Ted Corrigan. He's currently the CEO and General Manager for Des Moines Waterworks. And I heard a rumor that might be retiring soon. So early congratulations. Thanks for joining us.
4 more weeks, so it was good time.
Glad we got you when we did.
Yeah. I'll be pretty quick here. I want to talk about more specifically how some of what David talked about affects specifically one of the water utilities in the state of Iowa. So I'm going to take a little time and talk about the state of Iowa, where we are in that, what that means for us from a water quality perspective, kind of where we are today, and then give you some highlights from the emails that I've been getting this week while I was traveling about what's going on at home right now. So if you want to go to the first slide, just for perspective, Iowa's an agricultural state. Next slide. 23 million acres of row crops. Next slide. Also one of the most changed landscapes on earth. People say that all the time, but almost every acre of Iowa has been completely changed from what it was 150 years ago. Next slide. We are right in the middle of the Corn Belt, and if you go to the next slide, you can see that even in north central Iowa, which is be important in a minute, is kind of the epicenter of the Corn Belt here in the United States. Next slide. And we are also in what I would call the drainage tile belt. David talked a little bit about drainage tile, and on the next slide, I have something that's kind of duplicative of what he showed, but we're lowering the water table across the state of Iowa because corn doesn't like to have its feet wet. So we have a lot of drainage tile in the state of Iowa. In fact, if you go to the next slide, you will see that this is a map that shows the drainage districts, which David also talked about. North central Iowa is almost completely covered with drainage districts, which are governmental entities that help landowners band together to drain their land because their land is so flat, they don't have a creek or a ditch to drain the water into. So if you go to the next slide, you will see that we really practice drainage on an industrial scale in the state of Iowa. And the next slide is just another example of this. In Iowa is not a point source discharge, in case anyone was wondering. This is on point. So next slide. And this is another really interesting thing. This data is a little bit old, but this is a map that shows percentage of acres rented as opposed to production by owner. And again, north central Iowa, the red is, you're pushing 70% rental there. And there are reasons for that we won't get into today last time, but it's important from the perspective of Des Moines Waterworks and the implementation of conservation specifically. So next, now I want to talk a little bit about Des Moines Waterworks, which is my utility, has been for the last 35 years. Des Moines Waterworks is the largest utility in the state. We have about 600,000 customers who receive our water. That is 1/5 of the state of Iowa's population. We serve these 4 counties here, which, as you can see on the next slide, well, a little more about us. We have a conventional treatment process. We are a surface water source, which is important because we have no other option. There's no aquifer available to us or anything. We have to use surface water. And these are the surface waters that we use, the Des Moines and the Raccoon River, and they drain kind of the western half of what we call the Des Moines Lobe, which, if you were paying attention to the earlier slides, all the intensity in Iowa, be it agricultural drainage, be it corn production, be it whatever it is right there in north Iowa. I didn't include some slides about confined animal feeding and other things that are also sort of concentrated in north central Iowa, as is ethanol production and so many other things that we receive because of where our source waters lay. Next slide. So what's the result of that from a water quality perspective for a drinking water utility in the state of Iowa? Well, first of all, and one of our biggest challenges is nitrate. And this is the average annual concentration of nitrate in the Raccoon River at our intake since we started tracking in 1974, which is about the time that the drinking water standard for nitrate went into effect. And it's incredibly variable. I mean, you can see that it varies, mostly dependent on, flow in the river, timing of rainfall, and what's going on the landscape. But more importantly, the trend line is up and has been for a long time. And if we add this year, we'll only move it up further because we're having pretty significant challenges. Nitrate is one of our biggest challenges. The next slide. And that's because of some of what David already touched on. The tile lines in the state of Iowa, especially north central Iowa, tend to short circuit the water cycle. So rain or precipitation, snow, whatever it is that falls on the landscape, instead of moving through the soil profile and coming out in rivers and streams, it short circuits. And it picks up everything that was in the soil profile, but there's no opportunity for that to be degraded or removed as it moves through the soil profile because it doesn't move through the rest of the soil profile and it gets right into the. So on the next slide, that means for us that we have to do nitrate removal. And we have a conventional treatment process, which I mentioned, which doesn't do anything to remove nitrate. So since 1992, we have had an ion exchange nitrate removal facility at our facility that we use only during times when nitrate concentrations in our finished water are going to exceed that 10 milligram per liter standard. Next slide. Challenges with nitrate removal. It's probably not the best available technology. First of all, RO is probably a better technology, but not if you're lime softening with conventional treatment ahead of what you're doing. So we're sort of stuck with ion exchange. It's expensive. It costs us about $16,000 a day to run this facility when we run it. And it has a very challenging waste stream. Historically, we just sent the waste back to the surface water because we're removing, there's this much nitrate in the river, okay, on any given day, and we're removing this much, putting it back in, and we thought that was okay. It was for many years, but more recently, the DNR doesn't allow us to do that anymore because of the fluoride that's in our waste stream. It's a ion exchange, it's a salt brine regeneration, just like your home water softener. So it's a very challenging thing, and even more challenging now that we're sending it to the Wastewater Reclamation Authority. They've told us no more. We can't take any more of this than you're sending to us on a daily basis now. So as capacity or demand for water increases, or as if the standard would happen to go down, we really don't have anywhere to go with that. We don't have the ability to use RO in this facility. We don't have the ability to just double or triple or quadruple the size of that facility and get rid of the waste. So that's a real challenge for us out there, kind of looming from a nitrate removal perspective. The next slide. The next thing down that same path is that we're starting to see harmful algae blooms all over the state of Iowa, including in our source waters on an annual basis. And unfortunately, especially this year, today, this week, earlier in the year. And if you bring the next picture in, this is Saylorville Reservoir, which is just upstream of our intake on the Des Moines River. And that beautiful green grass is not grass, that is water. And no, it is not supposed to look like that. It does every year look exactly like that in Saylorville Reservoir, which is a federal flood control reservoir just upstream from our intake on the Des Moines River. Next slide. And those algae tend to produce toxins, and in our case, microcystin. And this is a chart of microcystin since we started tracking microcystin concentrations in 2015, right after Toledo, Ohio had the incident that they had with water from Lake Erie. This is the EPA's health advisory level, 0.3 parts per billion for preschool age children. You can see we spend quite a bit of time about that health advisory, usually late in the year, August and September, until this week. In fact, we've been at 1 part per billion at our intake on the Des Moines River for about 10 days in a row now in May, which is frightening. So nitrates on the Raccoon River are almost double the standard, 17 milligrams per liter today as I stand here. Microcystin on the Des Moines River is at 1 part per billion, which is 3 times the standard. So our operational guys are blending the nitrate out of the Raccoon with Des Moines River water that contains toxins, and they're blending the toxins down with Rackham River water that contains nitrate, and we're trying to find a balance there where we can get a source water that we can treat and deliver safe water to our customers, and that's a daily thing for us in Central Iowa. So, as I said, Iowa's an agricultural state. If there were no biofuels in Iowa, there would still be 10 million acres of row crop. But I do think it's interesting to note that, this is 2024 data from the Iowa Corn Growers Association. 23 million acres of row crop, 13 million corn, 10, More than 60% of the corn grown in Iowa was used for, ethanol production in 2024. And that, I think, aligns with the statistics that David shared. So it's a big part. 30% of the ethanol that's produced in the United States, used in Iowa, using 60% of our corn. Next slide. So, on our Zoom call, the question was, well, what are the opportunities? What can we do? And there are a lot of things. I think the science is there. The nutrient reduction strategy is filled with opportunities. None of these things will be surprising to you. They're known opportunities of things that could be done. I think the challenge is that they're not done. They aren't being done. And there's no, especially in Iowa, there's no political will to make any of them happen. I've been at the Waterworks for 35 years. I've been in this job for 6 years. I get this question all the time. If you could wave a wand and make something happen, what would you make happen? Well, the thing that I would make happen is that there would be some sort of an expectation that the nutrient loss or the pesticide loss or the chemical loss from every acre would be managed in some way. There would be an expectation. I won't tell you how to do it, but you have to do it. Do something. And right now, sadly, because of political will and land ownership versus rental and just kind of the paradigm that we exist in the state, nothing is done on most of the acres. Statewide. So next, couple of things that we have tried to do, just kind of click a couple more times through some things that we've tried to do with education and outreach and whatnot. And the last slide I'll share is just we've sponsored this cover crop seeder and field days, and we're trying to do things to incent the types of practices that we think will help with some very limited success. But anyway, I'll leave it there. I don't know if I'm over time or not.
I'd really appreciate your perspective. And for those of you that might not be from the heartland of the country, hopefully you're getting some perspective on Iowa. Now we're going to move to Illinois. I think Iowa is #1 in corn production, yeah. And I think the other fun facts that I've heard from my fellow Iowans is more hogs than people.
Yes, way more. Number one.
And Illinois is #2 in corn, but #1 in pumpkins and #1 in horseradish. So there you go. Fun facts for today. Our next speaker is Vijay Singh. He is founder professor in agricultural and biological engineering. And he also is the executive director of the Integrated Bioprocessing Research Laboratory, University of Illinois Urbana-Champaign. Vijay.
Thank you. All right, continuing with the same theme of what David talked about and then Ted talked about, I'm going to also talk about biofuels and water use in biofuels. And I'm going to get a little more deep into the process and look at how much water is actually used in the process, and then what can we do to reduce that water use. Also, I'm going to briefly talk about how we can address some of the water quality issues related to biofuel production. Next slide, please. So there's a lot of misinformation in print media as to how much water is actually used for biofuels production. Some outrageous claims are made as to how much water is actually used. I'll give you a good example. 2006, a company announced that they are going to site ethanol, dry grind ethanol plant in Champaign County. One of the local newspapers said, well, it will suck out all the water out of the Mahomet aquifer. And that is not true. So we'll look into what is the actual water use and how does it compare with some of the other industries that are also heavy on water use. Next slide. So here is the dry grind ethanol process that both David and Ted talked about. When we process a bushel of corn, 1/3 becomes ethanol, 1/3 goes out as CO2, and 1/3 is converted into this corn oil and DDGS, which are the two co-products. So 1/3, 1/3, 1/3. Next slide. This industry grew at a very, very fast pace especially between 2002 and 2014. It went up exponentially because we needed an oxygenate in our gasoline supply, but now it has kind of tapered off because we have hit the blend wall. And this industry is not growing at the same pace. Next slide. Now, when we talk about water use in dry grind ethanol production, there are two kinds of water use. One is called the processed water. This is the water that's actually used in running the process. And then this is what we call the contact water. This is the water that actually touches the corn. But then we have non-processed water use, which is primarily going into cooling towers and boiler, which support the process, but this water never touches corn. And this is the only water that is put out as an effluent. The water that touches the corn never leaves the plant. It only goes out from the dryer stack emissions. So that's something we have to keep in mind. Next slide. We can do a very quick mass balance of how much water is coming into the facility. We know what's the moisture content of the corn. The technology provider knows what is the ethanol production capacity. They know what the heat load would be because ethanol production is the exothermic process. You have to cool down those fermenters. So they know how big of a cooling tower or what the recirculation rate in that cooling tower has to be. We also know what is the steam requirement to run the plant, and therefore we know how much water is coming into the process. We know how much water is going out with the products, ethanol, DDGS, and carbon dioxide, what goes out the effluent, and how much goes out as water vapor. Next slide, please. So here is our system boundary. This blue is the actual process, and these are all support facilities that allow this process to operate. So typically water is pulled out of the ground, goes through these multimedia filters to remove clay, sand, grit, and then it goes into an oxidation tank. And from there, it goes to 3 different places. The biggest use is the cooling tower, and that is to cool the fermenters, because when we make ethanol, it's an exothermic process. The yeast dies if we don't cool the fermenters, and that's why most of the water used is in the cooling tower. Small amount goes into reverse osmosis to give us very low solids, pure water to run in our boiler that provides the steam to the dry grind ethanol facility. We know how much condensate return is there, so we can calculate what would be the makeup water going through the reverse osmosis. And then very small amount goes to the dry grind ethanol process. Next slide, please. So here is a mass balance for 100 million gallon dry grind ethanol plant. Again, here is the water that's coming for the cooling tower, boiler, and process water. This is the effluent. This effluent, like I said, is the cooling tower blowdown and the washing of the multimedia filters, little bit of regeneration of the softener that feeds into the boiler. So effluent is cooling tower blowdown as well as the reverse osmotic reject. And here's the water that's going out in the products, and that's the water that's going out as water vapor. Now, if we do some calculation, we see about 65% of the water coming into the process is going into cooling towers. 15% of the total water coming into the plant is actually going for the process, and about 12% goes for RO. But if you look at these numbers and calculate, it comes out to be about 4 gallons of water for every gallon of ethanol produced. That is a standard number. It ranges depending upon the quality of the water that you're pulling out of the ground. That can go up to 4.5 gallons of water, but lately technology providers are further and further reducing this water in order to minimize that water use. And this is where a lot of technology is going in, is how can we capture that vapor back into the process and use it. In fact, one of the technology providers did build a facility where they're trying to capture some of this water vapor. Next slide. So water vapor this is from the dryer stack emissions. That's where 80% of the water that comes into the facility is going out as water vapor. Next slide. So if you look at some of the other industries that are water heavy, For a can of fruit, 9.3 gallons of water. Sunday newspaper, next time you buy Sunday newspaper, 150 gallons of water. And I think I saw somebody present yesterday, I don't know who it was, that talked about a pound of beef and a pound of chickens, and that number was like crazy, much higher than what we have here. Even for gasoline, we have to use about 2 to 2.5 gallons of water. Next slide, please. So now I'm going to get into how we can reduce water use, further reduce water use in dry grind ethanol facility. And this is a study where we conducted, where we use effluent, treated effluent from a city effluent process and used it for biofuels production. And what we showed is that up to 75% can, or 75% treated effluent mixed with 25% fresh water can give you almost same ethanol production as you get with DI water, which was our control treatment. Next. And this is the study that we published. Next slide, please. We also use cooling tower blowdown. If we can take the cooling tower blowdown and use that water for dry ground ethanol production, and we showed that up to 100% of cooling tower blowdown will give you same amount of ethanol production as DI water. So there are strategies that, next please, and we published this also this work, and we were able to show that cooling tower blowdown can also be used. Next slide, please. Go ahead and click couple more times. Yeah. So this is a study that was funded, the Infuse project by NSF at University of Illinois, my colleagues from Civil Engineering Board and Ward. It was a very big project to model phosphorus flows throughout the watershed. But my piece was to see how we can capture some of that nutrient runoff, that goes. So corn is what's being used for biofuels production. Corn has very high amounts of phosphorus in it. And all that phosphorus ends up in DDGS. And that DDGS is then exported to where the states where the non-ruminant animals are. And there's just too much phosphorus. The animal is not able to absorb all of it. Most of it comes out their back end, goes into the water. So the idea was, can we model the flows of phosphorus within the dry grind ethanol facility and come up with the technology to capture that phosphorus and recover that phosphorus and use that phosphorus as a fertilizer and put it back onto the land and create like a circular economy. And we were able to do so, like 100% of that phosphorus is going to end up in DDGS. Next slide, please. We were able to find out where this phosphorus is going, and we were able to find that most of it is in thin stillage. And we can use calcium phytate precipitation to remove that. All we have to do is add a centrifuge on the thin stillage line and do this calcium phytate precipitation and recover that phosphorus, which can then go as a fertilizer. We were able to reduce the phosphorus in DDGS by 70%. We even did the techno-economic analysis as what it will cost for the dry grind ethanol plants to install this technology. But because there are no incentives to do so, nobody's actually jumping on and trying to do it, but it gives you additional co-product and it can be used to reduce the nutrient runoffs. Next slide, please. Next. I think that's it. Thank you.
Right, our last speaker is online. John Holliday from Lanta Tech is online and will share with us a little bit more about biofuels.
All right, can you hear me okay? And let me see, can you see my screen? Oh, I'm showing the wrong screen, aren't I? So, question, am I able to share my screen? Let me see.
You should be able to.
How about that? Okay. Well, thank you. I appreciate this opportunity to join with you today and to speak a little bit from the perspective of industry I've spent a decade or so in industry and a decade or so in a national lab system in looking at biofuels and biorefining. I'm going to give a little bit different perspective than the one that we get from corn. Sorry, there we go. However, absolutely agree that in the United States, when we talk about biofuels, we are talking about corn ethanol, about 16 billion gallons, another 3 billion gallons from either biodiesel or renewable diesel, and 1 billion gallons or so from renewable natural gas that comes from digestion. And certainly where people need to use the biomass cultivation could have by far the largest impact of water use, as well as both directly, whether we're talking about agriculture or aquaculture, but indirectly with the fertilizer and power. I'm going to really focus on the process. My talk is really looking, though, at a more general process. Lonzatec, we are a biotech company. We do a process called gas fermentation. We have 6 plants that are operating globally that use our technology, and they're in Asia and Europe. And but I'm not talking about our technologies, more general. I do want to, though, expand what we think of what a biofuel is, to be more than just fuels that come from agriculture, and just keep in mind that there are a lot of other waste streams, whether it be municipal solid waste or industrial emission waste, or even potentially in the future as we look at CO2. And so we have this larger picture that we should be thinking about. Also, additionally, some water and can be significant comes from the actual chemistry itself. So as we think about the water in the biorefinery process, there's a lot of washing. In the pretreatment, there's all sorts of reaction medium that uses dissolved substance and the nutrients to transport. We have potential processes that are not used a lot today, but will be in the future, could be in the future, such as Fischer-Tropsch or methanol production or gas fermentation, that are all exothermic, as well as the exothermic reactions that were already discussed by David and Ted. During separation certification, we have more washing, more cooling with distillations. And of course, there's a lot of cleaning and sanitation that to help prevent the fouling and the scaling and the corrosion. So all of these things are adding to that. As we take a look at the chemistry, water is produced in many processes in that chemistry. That's because we need to remove oxygen, and that oxygen is removed by either dehydration or hydrogenation. Those are much better ways of removing oxygen than the alternative source, which is discarding it as CO2. And I say that because CO2 also loses carbon. A lot of discussion, more so in Europe and other places, on green hydrogen than in the US. And again, this is hydrogen production in general. Does have a lot of water that's being consumed. And I would say, as we look at processes of the future, that just people often draw the boundary wrong, and they don't really think about what is the full process and what is all the water that's being consumed during that process. Anyway, with that 3 slides of talking about some general things, let me give you a couple perspectives. And the first perspective that I would say in general, and not reflective of the group that spoke today that really think deeply about water, but people who are looking at biofuels and the production processes, the water impacts are almost always greatly underestimated. This is because lab and pilot plants use purified and sterile water that's not representative of what is economical when we're working in an industrial process. And they generally don't consider or miss the impact on the product quality based on the water. And, there's water impurities that do impact the quality of the product that need to be thought about. They miss the impact of water impurities on the equipment design. And this can have a big impact as well. We think about the materials of construction that we will use in our equipment is based on the water quality that we think will be in that area that we're producing. And finally, most of these studies don't consider what's the water availability 20 years from now. So a lot of the things that I do see in the literature, not from those who really think deeply about water, but from others, if implemented, really do greatly underestimate the economics, have very unrealistic siting that would lead to great water stress and then further harm the ecosystems. So it's something that we do really need to think about. I think the second perspective I'd like to add is that water laws are just not considered. Particularly in the Western United States, water rights are very complex. They're regional. And again, we need to think about those rights for what's going to be not just today, but 20 years from now when I'm still operating my plant, and including what's the water sourcing and so forth. I am directly familiar with not necessarily my company, but with companies that I work with that have found great places to site plants until they think about water. And then immediately they just can't continue to think about that. And that just understanding water rights and the complexity of water rights becomes really important as people think about, and I think in a more general sense, particularly as we get out away from the Midwest. Two other perspectives. My third one, certainly water management is critical, and Vijay spoke about that. I think Ted and David both spoke about that as well. We really need to maintain water quality as we build biorefineries. There are many examples where the water quality is harmed, and not just in the U.S., but thinking about opportunities that I'm aware of in India and other places where great damage has been done. Where we see organic matter depleting the oxygen levels. We see nutrients leading to the beautiful algae blooms that I think Ted showed, and then other chemicals that are toxic to aquatic life that the previous speakers have spoken about. So this analysis that really needs to be done is deeply matter. We need to take a look at these water resources, the regional variations, and I appreciate that the National Academies is looking at this from a regional perspective, but that becomes super important as we look at this. I think people need to be in their analysis using more water stress indices and thinking about those mitigation strategies, including things like what Vijay has spoken about, and keeping life cycle water assessments in those, and maybe doing a better job of reflecting the cost because they do have an impact and are missed. I think my final perspective here is that energy and water do and must work together. When we design a plant, you design a plant with water treatment and recovery in mind. And it does dramatically change the cost of the plant. There are some positives in that we can capture energy in our wastewater treatment. Oftentimes, Lonzatec facilities are built perhaps at a steel mill using industrial waste that they use as our feedstock. They're not able to treat water, so we typically bring in our water treatment as part of our inside battery limits of our designs. And we capture that energy, but we also capture the nutrients. It becomes really important. You have to get some value from everything we do, but there's also a lot of extra cost. I think Ted talked about some of the extra cost when they have certain nutrients that they have to get rid of at times. And we see that as well as a general thing in the industry, where sometimes you're you have to clean up your water greater, or at least have a slipstream of that water that must be excessively clean so you can get the entire water into what's acceptable. So recycle becomes really important. We use recycle, most industry does, but it does add cost. And so if you are in a location that doesn't require recycle, it is less expensive to do that. And of course, to get the very most expensive part is zero liquid discharge. But as we think about this water management, we need to reduce that energy, think more about electrification and how that can be used. Mechanical vapor recompression, membranes, reverse osmosis are all things that can really help us think more about water, but we have to do it in a way that's much less expensive because water does add a tremendous amount of cost. So with that, thank you.
Great, thank you. Well, I hope that our speakers have convinced you all that when you think about biofuels, you also have to think about water, but not just water quantity, also water quality. So we've got 25-ish minutes or so for a panel discussion. I kind of wanted to kick us off from the perspective of really what brought us together, which is these regional energy water technology pilots, with technology defined very, very loosely and inclusively. I'm curious if our speakers can kind of kick off our panel discussion by sharing what technologies they think, and some of you have already shared a bit more about this, would be beneficial pilot projects to kind of break some of these feedback loops that we've discussed around, where we have energy in the form of crops and biofuels related to water, related to energy, also then on the treatment side of water. So I don't have a preference what order you go in. If you want to go in speaker order, that's totally fine, but I'll just open the floor and then we'll take questions from the room and online.
Yeah, I mean, I'm happy to start and kind of elaborate. Yeah, I mean, so I think from the quality side, I do sort of wonder about edge of field technologies and finding things that are broad spectrum enough to sort of capture and manage the complexity of the waste, but also affordable, low cost, highly scalable, because that's the limitation. So I don't really know. I think I've talked myself enough into thinking that limiting the inputs is probably the best way to sort of manage what's coming off the land rather than trying to invest in the end of the pipe. I think beyond that, I think there are anything we can keep doing to minimize water use, and I agree, like lots of gains have been made in that space, but then also managing the waste. A lot of these wastes are complex streams. There were discussions of like resource recovery from waste, even if it's just sort of reject water or cooling water regenerant that's going to be rich in a lot of things that still is it's brine, right? And so thinking about ways to manage the waste streams with low cost, low energy, pushing towards zero liquid discharge, even though that's really, something that's aspirational, but I think could be achievable if you're making big pushes. Those are things that come to mind. And then, yeah, the cooling piece. I mean, so much of the discussion, really the future in Iowa when it comes to corn ethanol, I think is going to be the CO2 sequestration. So technologies around how to make that compatible with water use in a changing climate. So even if we talk about water use coming down, like one thing we haven't talked enough about is we're not in it now, but Iowa just came out of a 4-year extended drought. And so why are communities punchy about new water use and growth in soybean crush? It's because they're seeing private wells dry up and they're seeing communities that are exploring wastewater reuse. That happened in Osceola, Iowa. And when I moved from California to Iowa in 2007 and was sort of laughed at because, or 2011, because my work in California was on wastewater reuse and everyone said, you're never going to wastewater reuse in Iowa. And we're already considering. So I think we have to keep pushing technologies that advance minimizing water use, reusing what we have. And I think it's continuing things that are already happening, but just not give up just with what's good enough and keep striving for more.
Me? Okay. From the perspective of technologies that I think would be interesting to use, it strikes me that there are a lot of technologies, a lot of options, a lot of the, some of the things I listed that are specifically related to trying to improve water quality, related to corn production, row crop production, that are not widely used at all today. And so I think that the technology we could use is possibly public policy that would incent or require the use of some of those technologies. We have 23 million acres of row crop, for example, and 3 or 4 million acres of cover crops in the state, where we've been pushing on that for a long time. So maybe some consideration there. Something else that I think would be interesting is, given that 60% of Iowa's corn is used for ethanol, if the ethanol producers would have some sort of minimum expectation of standards that the growers would use for their the inputs that they're going to use in their plant. That would impact 62% of the acres that are growing corn in the state of Iowa. And I've not heard that there's anything like that going on. You hear of other other industries or other buyers of certain products, and incenting their suppliers to do things in a certain way. And if the ethanol industry could get behind that sort of a thing and say, hey, we're gonna have some minimum expectations if we're gonna buy your product, it could be huge. But I don't hear that talked about. So I think of it in terms, less in terms of actual technologies that are things that you would install and do, and more as policies that we can consider to incent or encourage.
Yeah, so I highlighted few in my presentation. Now all these have been demonstrated only at the bench scale. I think it might be a great idea to take these to a pilot scale, where we are actually, maybe pairing up an ethanol plant, if at all possible. Obviously, some safety studies have to be done, but taking treated effluent from a city and using that to produce biofuels, would be something good. Then be using the water within the dry ground ethanol plant, like cooling tower blowdown or a boiler blowdown, and putting that, well, boiler blowdown currently goes into the process, but cooling tower blowdown, if we can use that and put it back into the process. And then there are multiple technologies that we have proven are very, very effective in trying to mitigate the nutrient runoff. And when we published this paper, and by the way, I only presented here for ethanol production, we have done the same thing, exactly same thing, in biodiesel production from soybeans. We have also taken corn that is used for wet milling process, that's for making starch. Some of that industry also takes that starch and converts that into alcohol, but that starch goes into high fructose corn syrups, and we have done that in that. And when we presented this to the industry, like I said, Integrated Bioprocessing Research Lab, it's a center that I direct. It's all about working with the industry. And we have over 130 industrial partners, many of them repeat customers that have gone through IBRL. And we do regular professional workshops and presented some of these ideas to these industrial partners. They were very excited. They wanted to do it. But because how the costing is, and then, we said, well, you might have a co-product that can actually go back to the farmers and be used as in fact, we partnered up with colleagues in crop sciences, where they took some of the, not struvite, but, this phytate, that the calcium phytate complex that we recovered, and grew plants on it and did very well. So I think those are some of the technologies that we know are proven. And if we do some pilots with that, and we can show that this can be done, provided there's also some regulatory support, policy changes, then I think we can make a very big impact. And I only presented phosphorus, but we can look at other nutrients as well. We can look at nitrogen. Corn itself has a lot of nitrogen in it. It's in the form of protein, but in process, what you can do is add a little bit of proteases, and certainly you open up that protein into amino acids and all that can be used for yeast growth and things like that. So there are so many technologies that are available that can reduce this nutrient loss in dry ground ethanol production. And not just in dry ground ethanol production, anything related to corn and beans technologies, similar aspects can be applied, and you can try to, at least address some of these water quality issues.
Excellent, thank you. John?
Yeah, thanks. I'd like to echo much of what has already been said, but particularly about from a cost perspective, we need to bring down the cost. Recycling water is something that we do as a general practice in our designs. It adds a significant amount of cost. Zero liquid discharge adds a very, very high amount of cost. We need technologies that can help us think through these things. I mentioned mechanical vapor recompression as one example of something that can help us reduce the amount of water that we're using in cooling towers and distillation. We just need better ways of taking a look at where water is being used and how can we less expensively handle those. I don't remember if it was Ted or David who talked about, I think it was Ted who talked about public policy, and spot on. It really is hard to get the full value that you need from the co-products that you can produce that make up for the cost that is being brought on. So we have several important co-products that we use, that we produce, and oftentimes in an industrial setting, people just say, yeah, not enough value, and we'll just use that for heat generation. So co-products can be are important, but they're also often overestimated and do not make up the cost difference that the technology that we're using to reduce water use is costing.
So a lot of these comments are shockingly similar to things that we talked about yesterday, actually. A discussion of a salty wastewater stream sounds a whole lot like produced water. And discussion of cooling tower blowdown sounds a whole lot like the water reliant power generation that we talked about. And that John's last comment here on co-products with not enough value sounds a lot like stranded natural gas. So it gives me actually some hope in this perspective that some of these technology pilots might actually have some unintended co-benefits around having an application in a context that they maybe weren't initially designed for. So I'm really glad that we brought all of these topics together in this 2-day meeting. I'll open it up to questions in the room, and if there's questions online, just raise your hand and I've got it pulled up. Looks like I'm starting with Nick. On to George.
Got a rather basic question for David.
Yep.
And Ted, I think Ted first mentioned this, and then you mentioned the drought situation. Stream base flow is primarily shallow groundwater. And we talk about these tile drainage systems, and you talked about lowering water table. You talked about a 4-year drought. I just looked at this morning, drought monitor for Iowa. Probably a third of the states have abnormally dry, and then some still in moderate drought. How is how do these tile drainage systems impact base flow in dry periods?
I'll let you start since you're not.
Yeah, I will start. The tile drainage systems, we believe, move the water through the system more quickly. And so when it rains and water's coming off the land, it intercepts that and it moves through the system more quickly. And then the tiles will stop running at a certain point. And so our general sense is that they're interrupting the water cycle, and so they're moving water out of the system more rapidly. And then when you get to drought conditions and lower base flows, you see lower minimum flows in the river because you've pushed all that water through the system sooner in the cycle. So that's our perspective. It's not something we've studied, but just conceptually, we feel like it makes it wetter when it's wet and drier when it's dry.
Yeah, I mean, I think the biggest challenge, so when it's dry, they don't run. And so when we get extended periods of drought, we've become reliant in some ways on those tile lines in normal climate conditions, pushing the land applied chemicals off the land into the waterways and making it a water quality problem. Ted's experienced this. When it doesn't rain, all those chemical inputs accumulate. And so last year, the nitrate levels across the state were massively high when it finally decided to start raining. So it's probably best in thinking about them in terms of drought. They're just not there to release the over application of chemical inputs in a drought, but those don't go away. A good chunk of them don't, and then we get these massive surges. And so that's why I think I did the numbers and you sometimes presented in talks. It's a massive amount of nitrogen loss that we had last year after all that accumulation for 4 years.
Yeah, we always think of it in terms of concentration and everybody
Yeah.
else looks at it in terms of quantity, but it was second highest nitrate concentration we'd ever seen.
And the largest nitrogen load export leaving the state since 2016, which was the last really. The crazy part about last year was it was a very wet, the rivers were high and still pushing high concentration. So if you do it on a mass load basis, it was quite large and fairly historic for Iowa.
Can I do a quick follow-up?
Yes.
So in wet periods, are these impacting recharge to the shallow groundwater system? These tile drainages, so that when you get to a dry period, the impact's already there. It's not, they stop draining, it's that
Yes.
your system's not recharged.
Yes. I mean, I would say yes. I mean, again, there's plenty of folks that have kind of looked at that and so maybe I'm speaking out of turn. I need to look at that literature a little more closely, but absolutely, I mean, they're very effective at doing what they do, which is getting the water off the land.
I'll add one more complexity to that. I don't know if you've seen this in Iowa, but I've seen it in central Illinois where we also have a lot of tile drains, very, very flat land, tile drained land in row crop production. But in the event of drought, every so often, a farmer will invest in center pivot irrigation. We're primarily rain-fed ag, but then once that farmer has invested in center pivot, both center pivot irrigation and tile drains all on the same field. And once they've made that investment, you can bet they're gonna use it anytime there's a deficit and rainfall. So there's some compounding things happening there.
And that is happening. I think
Center
the
pivot.
irrigation line is moving east, right? And the drought that you're seeing is primarily historically concentrated in western and northwestern Iowa. Making water access a challenge both for crops and for hogs. And so we've solved the hog issue by a big water production facility out of state that pumps in a regional water, but I think more are turning to things like irrigation, further drawing down aquifers. And once they're there, the yield increases they see, it's sort of sold as climate proofing, right? So in those drought years, they're still maintaining yields.
Okay,
Well,
Jordan and then
I
Jordan.
appreciate that.
Thanks very much for your talks. Very interesting. I have a question about what you sort of see as a trend or emerging issues. So, BJ, I think you showed corn-based ethanol production is pretty stable at this point, largely because gasoline consumption is stable in the United States, that we've hit the blend wall. And then, I think projecting forward, gasoline demand is going to be indirectly related to light duty vehicle electrification, right? So that's to the extent that to which we electrify vehicles, demand for gasoline and corn-based ethanol could decline. And then, David, you brought up sustainable aviation fuel, which seems to be sort of the way ethanol producers may pivot. But then that's a policy that could go away and may already be gone. And then there are strict emissions reduction requirements related to that, right? Which corn-based ethanol has struggled to hit. And then there are ways to reduce that, but there's a pretty steep cost versus emissions reduction trade-off there. So I guess I'm curious if like a long-term decline in corn-based ethanol demand is a scenario that's discussed, and how that might influence some of the water quantity and quality issues that you brought up in your talks.
And I've got things to say, but I'm happy to let you speak first, DJ, because we've been talking over here.
Yeah, so, certainly, there's definitely export markets being developed for ethanol. So there's a lot of ethanol that's currently being exported out of US. But certainly ethanol industry is looking at producing sustainable aviation fuels. But in order to meet the carbon density values, you have to sequester that CO2, because the ethanol that is leaving the plant itself already has too much of carbon intensity that it cannot meet the SAF guidelines. So unless you are putting it in ground and you're below 30 carbon density, then only making SAF is possible. But a lot of ethanol plants are looking into that. Another thing that's happening that we are noticing, especially in dry grind ethanol production, is that they realize that ethanol is not going to grow as an oxygenate. So what's starting to happen is many of the dry grind ethanol plants are looking into retooling themselves to produce dextrose, dextrose,
Okay.
not producing ethanol. And that dextrose, there's a huge demand for dextrose for the industrial biotech. So right now, all the dextrose that is going in precision fermentation, which is used by all these companies that are making eggs, milk, meat, fur, whatever from precision fermentation, all that is currently going out of the wet milling industry, but they have limited capacity. Even like textiles, renewable textiles and things like that, plastics and all that. So there is going to be a huge demand for dextrose going forward. And there's already a technology provider that is offering what is called clean sugar technology, and they have already retooled a plant in Iowa to produce dextrose rather than producing alcohol. Some of these dry grind ethanol plants have also pivoted towards other biofuels like butanol and things like that, rather than producing alcohol. So there's at many fronts this work is going on. Obviously SAF. LanzaTech has already put a facility in Georgia that is SAF, making SAF from ethanol or from ethanol. But there are others that are looking into it, but there's other possibilities as well.
Sorry, what's the dextrose used for?
For industrial biotech. So I don't know if you have tracked that precision fermentation is growing like crazy in US and around the world. And what that means is you're using sugar to produce things that used to come from conventional agriculture. Like, conventional agriculture, we produce milk, egg, meat, all these things can now be alternatively produced by precision fermentation. And many countries around the world, for example, we have a very large project from Singapore, because Singapore is a very small country. They don't have any land to grow agriculture, do conventional agriculture. And what happened during COVID is that they used to import all their food into Singapore, but the countries that they used to import from, they said, well, no, first we need to keep it for our people, right? So that was a national threat for Singapore, and they decided that by 2030, 30% of the food in Singapore will be produced in Singapore. And it's all going to be produced through precision fermentation. So there's going to be a huge demand for dextrose or from sugars, because you feed the sugars to microorganisms, you can retool the microorganism, change their metabolic pathways to produce a metabolite at very high rates, tighter in yields, where it by itself or in combination with chemical catalysis can replace a lot of petrochemical products. So that's where, and this is already starting to happen. As I mentioned, one dry grind ethanol plant in Iowa has been completely retooled to produce what's called clean sugar.
So
I think John wants to add something too, but go ahead.
So one thing I'd say is that Iowa's resisting any shift away from corn ethanol as much as possible in their policy. So we have year-round E15, right? Not worrying about air quality impacts that have long let us not want to do that in the summer. We're pushing it. We passed laws that require ethanol infrastructure at every gasoline station, whether people want it or not. We are pushing back on installation of solar because we don't want to take away potentially productive cropland that has a certain corn suitability rating or CSR score. And so we're not building photovoltaics the way we could. We are behind on electrification infrastructure for vehicles. And so I want you all to appreciate that at the state level, we are holding on to corn ethanol at the expense of other opportunities to transition away to more sustainable energy production. And so that is a challenge. And so SAF will be the future. They've been talking a lot about the carbon intensity market in California. Like that is what's really driving a lot of this, and they make no bones about it. And they do. There was just a quote in urging the governor to cancel to veto the pipeline bill, where one farmer was talking about the corn industry. right? And thinking about it as its own sort of stand-up industry in Iowa, just the idea of making corn. So I want to make sure that's, yeah.
John.
Yeah, thanks. Just two comments from an international perspective. A lot of countries do not, Europe in general, very hesitant and usually puts caps on the amount of fuels that can be used from agricultural food products. Whether or not we agree with that is not the point, but that's just the reality. There is that kind of stuff that's looked at both from CORSIA, which is looking at sustainable aviation fuel, and others, and how it will be used. Nevertheless, I'm certainly aware of many, Marquis, for example, who exports quite a bit of their ethanol to Europe. But the huge growth of ethanol production that was attributed to oxygenates, it really should be attributed to the renewable fuel standard and getting a renewable identification number. It's 100% correlates with policy and those policy drivers. So what do I think is going on in the future? I work for a company that spent a lot of time of taking the ethanol that we produce from industrial waste and making, addressing the ethylene value chain and making products. We still think that's really important. It's really hard to make that work outside of niche markets right now, when you have regulated markets that are fuel markets that are so much easier to get to cover the green premium that still exists, right? So regulated markets really will continue to be the future. And those regulated markets generally are fuel markets. So
I see that we are 1 minute over our scheduled time. Can we take the 3 questions in the room? And Jordan, you put your name tag down, so you.
My questions were covered. This is great.
Perfect. Okay, so we'll do Shelley, Kirk, and then Peg, because that's the order I saw you put your name tags up, and then we'll go.
I was just curious, so for those of you who weren't here yesterday, I'm Shelley Chard. I'm the Water Quality Division Director here at Oklahoma DEQ. So I live on the policy side. I'm very curious of the tile drains and the impact on the municipal drinking water sources. Is there any talk or partnerships of either trying to figure out how to recycle this water for ag purposes or treatment to try to reduce the cost on the ratepayers of the drinking water system? I'm sorry.
No, interestingly, on the recycle perspective, during the drought, there was some talk about, capturing tile drainage and saving it on the landscape so that it would be available for, potentially for irrigation or whatever. I haven't heard any talk about that since it started raining last spring. So, that's one of those things that kind of comes and goes a little bit. But more interestingly, from my perspective on the, the regulation or whatever, in 2015, Des Moines Waterworks filed a lawsuit against some drainage districts in our watershed, claiming that their, 48-inch diameter discharge points from the county tiles were point sources. And that was extraordinarily controversial in the state of Iowa. And legislation was introduced to eliminate our board. And, commercials ran vilifying our general manager, and it became, and it still is, just kind of a us against them war again on, the water utility who would dare to suggest that the discharge from agriculture had any negative impact on water quality for the citizenry, and it shouldn't matter. And so there's just generally speaking in the state of Iowa, there's, David talked about the things related to ethanol and requirements, but the same thing exists related to just about any kind of regulation of agriculture in any way, shape or form. And so there has been some talk, but it was met with extraordinary resistance. And I don't see the political landscape has gotten worse, I guess, the term I would use there. But less likely or more resistant to regulation since then. So that is just not gonna happen.
I mean, the other thing that we haven't talked about that's important in this context, since so much of our water quality challenges come from agriculture, and that's tied to ethanol production. Right now, Iowa has the second highest rate of new cancers in the US, and it's one of the only states that's rising year on year.
Mm.
And a lot of this has been tied, there's lots of research that has shown nitrate and the Safe Drinking Water Act standard is not protective enough to account for these chronic health level effects. Ted has dealt with consumers that don't want to drink his tap water because they think it's making them sick.
Sure.
This is the intersection of when you don't do anything or you rely on treatment technologies for 30 years without actually trying to change source water protection. That now we're at a point where people are losing faith in their utilities, including the best ones we have in the state, like Des Moines, because of health concerns. So it's unsustainable in that way in Iowa. And we're headed towards a pretty headed towards a pretty like bleak place if we're not able to fix this soon.
Yeah, I guess my thoughts are maybe more of a comment than a question, but just how appreciative I am of this. And I think how water quality is such a through line here when we talk about water energy nexus. And I guess I was going to add how it even connects even more. I mean, Ted, I appreciate your thought from a waterworks perspective, but it's the same story from like a power production standpoint, right? Where you've got these unregulated non-point source discharges that are going into a river system. When I just look at the power industry perspective, but I think what I'm about to say would be same for anybody who's got regulated NPDES discharge or local receiving water body criteria. I mean, as that water quality degrades in a river system, when you're bringing that into a facility, I mean, that increases cost on the treatment of that incoming water, but then you're also heavily regulated on a discharge standpoint, right? So, we've talked some about like thermal discharges and stuff, but it's the same with aquatic toxicity and things like that, that really the cost of that's getting borne at the site that's either our production site or you guys. I mean, part of y'all not being able to send that water to the POTW is probably because of their regulations and what they can discharge back to the river. So it's all being borne through there, even though the water quality drivers are so much on the non-point source side. So I just appreciate the conversation because I think it really ties together so much of what we've talked about in the space of people who are part of Water Energy Nexus who are somewhat driven by regulation. Maybe they're effective, maybe not, but kind of seeing the other half of the coin today really adds a lot to the conversation.
Right. Let's go pay for our last question.
So I'm really excited to hear all the talks today and also the connect dots with yesterday's discussions. Because during yesterday, we discussed about the energy water nexus is multi aspects, multi-facets, it's all interconnected. I'm just thinking, yesterday we mostly talked about produced water treatment and reuse, especially in the Permian Basin, because Eric and I, they all come from the Permian Basin. But actually, Ohio is also a major oil and gas producer in the United States. And then we talk about to use the treated produced water for agriculture irrigation. Maybe there is opportunity to use alternative water for corn production. And also we have the same challenge is water quality and also resource recovery. And we also involve the nutrient management because, for example, for the produced water treatment reuse, we have the huge amount of ammonia. You may not realize ammonia is in the produced water as well. And it's even higher than wastewater centrate. And so we discuss about how we can recover ammonia as the struvite or fertilizer. We are lack of phosphorus. We need to add phosphorus into it. But for biofuel production, you have a lot of phosphorus. So I'm thinking there are a lot of synergies related to it for circular economy and also for carbon sequestration and capture. Produced water can be used for that purpose as well. So I'm thinking how we can connect all the aspects for a regional demonstration. I just feel everything can be connected. And another question is related to the level of skill, because do we need to build a centralized treatment facilities to connect all of them, or it will be decentralized? How we will connect all the dots together?
That's the hard part, is connecting the dots.
Yeah, I mean, I think using alternative or lower quality water sources where you can makes sense. It's just, where do we have them in Iowa that they're easy to get to where we're actually producing? I mean, so maybe there's a way, since a lot of these CO2 sequestration facilities are gonna be right there, at least that's the vision, I think, to have them with the ethanol production that, there might be ways to really smartly design those so the two can work hand in hand, right? And maybe that's being thought about, I don't know, but that from a water perspective, there's opportunities there because you'll have the waste stream, you'll have the sequestration, so.
And no question or comment, just a quick request. We have a great idea for produced water and I'm looking for samples if anybody can.
You're in the right place.
Get you some from Alabama.
Great. Well, let's give a round of applause for the. Thank you. I mean, I've been a water manager much of my life and that was one of the scarier water quality reports I've ever heard, so. Right, well, we're scheduled to have a break at this point, I believe. Is that right? Or no, we're going directly into a facilitated group discussion. Is that right? If you need to run out, go ahead, but.
I'm gonna need coffee.